area is covered with time. Okay, so what I'm going to draw is the slider. Okay, so this is time equal to not equal to 0, and then the slider move to here. This is the area. Am I right? Does that make sense?
Yeah, that makes sense.
Yeah. So if I do here also, right? If I do here also, so the slider is parallel to the shear flow axis. So this is the first slider, second slider, right? Third slider. So it covers the area already. Can you see that?
Oh,
Right. That's
got
it.
it. Okay.
Okay.
Yeah.
Yeah.
Alright,
So
thank you.
mathematically, that is happening. Okay.
Okay.
Mathematically.
Yeah.
So the reverse flow also is a mathematical
Oh,
restriction.
makes
Okay.
sense. Yep.
Right. Yeah. So you can see this shear flow or shearing stress. The formula is really easy, right? It's the analysis. Okay. A lot of times students don't get it, or when I'm teaching this, they find it difficult because of analysis. Two formulas. Okay. Right. Like what was there? Two formulas. And you guys are, yeah, Eugene, for the past 4 weeks, we've been staring at two formulas. Indeed, you have. Okay. So the next one. Now, what I've just thought is the most complicated expression that you can see in analysis. Okay, so this will be slightly easier because you are exposed to all the rules now. Okay, so we are going to look at unsymmetrical loading. Yeah, unsymmetrical loading. Of a thin wall member. Okay, highlight thin wall. Okay, so I'm going to you guys have all these diagram which I posted. I'm going to show you what is symmetry bending first, or symmetry loading. Okay, right. So over here, I'm going to copy the other diagram. Okay, so what you see over here, so this chapter, as I said, is unsymmetrical loading of a thin wall. But let me show you what is symmetrical loading first. Okay, so then later on I show you unsymmetrical. So this is symmetrical loading. So if you look at this diagram, so if I'm going to label this our X, this will be our Y, and over here will be our Z. Okay, so the when this structure is bent, which you see it is bent, right? You can see from it's not really our exaggerate the load. Okay, the deformation. Okay, so this is exaggerated. Okay, so this is like I have to be careful down here. So this is like exaggerated. Okay, so this will be horizontal. Okay. Okay. So the bending or the deformation is only on the XY plane. Okay, so it's only on the XY plane. Okay, so if I highlight that plane, okay, so the structure will deflect on along the XY plane. Okay, along the XY plane. So when that's the case, right? So this is the cross section now. Okay, cross section. So if we look at the cross section, so this is our Y and Z rotation on our X. So the shear force is acting exactly vertically, right? As you can see, and you have a what we have over here is we have a moment which is equal to P times a certain distance X, and you have a shear flow which is V, which is equal to P, right? So the most important thing, if I draw an axis, okay, over here, the left hand side is equal to the right hand side, right, in terms of geometry, right? So we can see when this is the case, right? You have stress X is equal to minus mz over izzz y, and then you will have your shear in the xy direction, right, is equal to vy over izz qz divided by t, right? So equation 1 and equation 2, right? So we know that equation 1 is based on symmetrical. Just to quickly recap, bending, right? That equation only can be applied for symmetrical. However, equation number 2, right? Equation number 2 is only valid under when there there is no twisting or rotation, right, about the z-axis, sorry, x-axis. Okay, right? So the deformation, so x-axis, right? So there when I say twisting, this is what I mean by twisting. Okay, so if this is our, this is still our V, right? So this is what I mean by twisting. So there's no twisting, okay? And this is only possible, without twisting, is only possible when it is what? Symmetrical, okay? When the geometry is symmetrical, left is equal to right. Now, then I'm going to show you the condition, okay? So this one is, I need to write down symmetrical loading. So this is the condition of symmetrical loading, okay? Right, so there's no twisting. Now, I'm going to show you another situation where the deformation will twist, okay? So is the next image I'm going to, so condition of symmetrical loading. Okay, so I'm going to take this diagram, the one below, which they did the twist really well. Right. Let me pose the cross section again. Okay. So now what you see over here, right? So I'm going to draw my transformation again. X, Y, and Z. Now, for this condition, you see, right? You have unsymmetrical. Okay, is what we call unsymmetrical loading. So we call it unsymmetrical loading is because the deformation is along the XY plane and a rotation, right, or twist about the X axis, right? So you will see that the structure will want to rotate, right? We can call it rotate, or you can call it a twist, okay? So the reason why, right? So if again we were to draw, if I were to draw the axis of the structure centroid, right? So we know that this is the centroid, right? And I'm going to divide this into left and on the right, okay, right of the centroid is the right. So you can see the left has a what? Higher stiffness. Right? The right has a what? Lower what? Stiffness. Right? Yes, a lower. Why it has lower stiffness on the left hand side? There is no web. Right? You got a gap. Right? You got a gap where I highlight in yellow, right? You got a gap down there, and there's no web. Whereas on the left hand side, it has higher stiffness because it has a what? There is a web. So for this reason, right? For this reason, the deformation, right? As mentioned before, deformation, right, has an additional twist. Okay. So when that is when that's the case, okay, this makes, okay, so the twist, okay, this makes tau equal to VQ over IT invalid, right? Because to apply this, right, when we were analyzing in terms of math, right, we did not have a twist, right? So this is pure, this is only deformation without twist. Okay, right? So you guys have learned if there's a twist, there's another formula which we can incorporate, which is tau is equal to TR, right, over J, right? So this is torsion, right? This one is due to torsion. right, due to torsion, right, and the deformation